So I like to talk why our framework is unique and more general. So if we fix the omega-1 in our framework to be an identity matrix, our framework reduced to existing method in the multitask learning literature, which is known as multitask relationship learning. So in this setting, they try to model the correlation among tasks, but they don't try to model the correlation among different features. So if we fix omega-2 to be an identity matrix, so this reduced to another setting in the multitask learning, which is called multitask feature learning. So in this framework, they try to fix the relationship among tasks, but they try to model the correlation among features. So if we let both omega-1 and omega-2 to be identity matrix, this reduced to a single task learning setting, which is basically a ridge regression problem. To tackle the problem, knowing the fact that our optimization framework is a biconvex function, so we can use coordinate proximal gradient descent to optimize it. And also, notice that in our framework, the constraint is an open set, which requires omega-1 and omega-2 to be positive definite. This is an open set, and it's not compact. It sometimes can create a problem because we need to use coordinate proximal, which includes a projection operation. Projection onto an open set is problematic, so we use a gap parameter delta I to, instead of projection into the open set, we project into the delta positive definite cone, and then we tune the parameter delta using solution paths. So in brief, we use a sequence of decreasing delta with each delta t, we use the solution from the last iteration as the initial point for current iteration. And we can show that the sequence of delta will terminate in a finite step. Then Renato will introduce our experimental work.
So to validate our models, so we consider two types of data: synthetic data, where we actually generate sigma 1 and sigma 2 and sample the weight vector from the prior, and generate a linear model, adding some Gaussian noise, described as here, 10 tasks, 200 instances per task, 100 features. And the other one was the brain data, where you actually regress from word features, so each person observes the same set of words with the same set of features, semantic features, and you try to regress to the brain voxel activation, which is different between different people. And we treat each person as a task. So this is a data set from Tom's group. And so we compared our model with the three other models, which are special cases of ours, as Han described, when sigma 1 is fixed to the identity, with the sigmas fixed to identity in the various cases. So the first one is our model. The second one is, I think it's by the same order, which is like the first one is for sigma 1 equal to the identity. The third one is with sigma 2 equal to the identity, and the other one is single task learning, where you don't capture task relationships. And okay, so what we've seen is that multitask learning helps, but our model didn't perform so well in the synthetic data. I think we can do a better job here. And in the brain data, it was kind of difficult to get good results anyway. But multitask learning still helped a bit. And so these are the conclusions. We propose a new multitask learning framework which captures previous existing frameworks. We develop algorithms to optimize it. And we see that multitask learning helps, although our model didn't perform so well, but we are still working on it. And we hope to, and we apply it to a brain data set. And these are future extensions. So kernel extension and a hierarchical model, which has been looked at in the paper by Alex, actually. So thank you. Questions?
So we have time for one question.
Is there any other kind of relaxations when you transform to a non-convex problem to a convex problem?
Yeah, it's a good question. So I think there is a way to transform the middle term, which is the correlation among features and tasks, to relax it into a convex component. But the problem is it's not tight, which means we cannot achieve the equality. And the other problem is that term is actually the unique term in our framework. So our framework is trying to model the relationship both on the task dimension and also the feature dimension. And that term exactly model the complexity. And on the other side, the reason why we just relax the concave term is that after relaxing the concave term, we can show that the effect of the concave term combined with the effect of the second term constrain the optimal solution to be interior of the positive cone. So without the third term, it's not guaranteed that the interior is in the optimal solution is in the interior. It can have it in the margin, and this is problematic.
Yes.
Sorry, guys, no more questions. We run out of time.
Oh, we can talk offline.
Yeah, you can talk after that. So I would like thank you again. Like the second team, we have said we need to collect forms for team 1.
Oh, that's not us.
I just sent it to you. No.
I've done it down once.
Yeah.
Alright, there we go.
Yes. Okay. Slideshow.
Or rush through my part.
Yeah.
Like I'm
This one, later we need to pass it around, right? Is it special?